So, hello again. In the previous lecture regarding artificial intelligence, we began with adversarial search and game playing, right? So, in that lecture note, I gave the motivational part in which we discussed why do we need to study game playing? What is the necessity of studying that? Now, uh, in engineering practices, we require game playing. All right, it actually gives the simulate. It helps us in creating an environment where we can cope up with the mistakes that might happen or that might eventually happen after the design of the equipment that we want to build has been completed or something like that. So today we will discuss the Minimax algorithm. All right. So in this algorithm, what happens here is just like the tic-tac-toe game that we discussed in the previous lecture, we are going to take into consideration that we are only going to have two players. Okay. This algorithm that we are going to discuss today is for only two players. One is Max and one is me, just like the same scenario that we discussed in the previous game. So what here is, there were certain parameters that we described regarding the tic-tac-toe game in the previous lecture. uh, what were the parameters? Number one was the initial state. uh, the things that I'm talking about is covered in the topic search applied to adversarial games. All right, number one is the initial state, which represents the current game state. All right, number two are the operators. Given a game, there are certain number of legal moves that a player can make. All right, so number third was the terminal node, which describes the end of the game. So each of those terminal nodes, what happen is it has a certain value associated with those terminal nodes. Those terminal node values describe whether the player has won or lost, or both the players have a draw situation or something like that. So the fourth is the utility function, which was also known as the payoff function. So the utility function gives the value of the outcome of the game. So for the tic-tac-toe game, how many utility values did we have? We had three values. One was -1, one was 0, and the another one was +1. So if we consider those three values for a player like Max, -1 would describe that Max loses the game, and 0 is the instance where both the players Max and Mean have a draw situation, and +1 describes the state where the player Max wins the game over the player Mean. So that was the discussion we had in the previous lecture. Now today what we are going to discuss is the Minimax algorithm. So this algorithm in principle uses recursion or backtracking algorithm. Now before we start to understand the working of this algorithm, we are going to make use of a game tree. Alright, a game tree is very simple, but it is a tree that describes the legal states of the game, possible legal steps of the game. So we had a description for the tic-tac-toe game. Remember guys that I shared a diagram in the previous lecture. We had a game tree for the tic-tac-toe game. So for understanding the working of this algorithm, we will also take into consideration another game tree. All right, let me show you here. Don't worry about the notes, I'll share you in PDF format. So we have here a game tree. So here in this tree, what is given is say let's start, the game starts with an initial state A. All right. Now in this initial state A, either the player max or min has to begin the play, taken into account that the step it takes should be a legal move. All right, there should not be any unlegal moves in this game. The Minimax algorithm works in such a way that both the players max and min play in a fair manner. All right, that means either the player max or min does not try to cheat the game, but they play in a very fair manner. All right, in our analogy, what we will use is we will use the term optimal. All right, each of these players, max and min, which are going to play as opponents to each other, they are going to play in optimal manner or or in fair manner to each other. So given in this tree, let's take into instance that in the initial state A, the max player begins the game. All right, when max starts with the initial state, it again generates another two legal states which the mean player can make. So according to this, the last move is made by max. All right, in this game tree. So after this, the possible terminal nodes are also generated. So this is a very simple game tree that we are taking into account. All right, a general game tree would have a large depth or a large height of the game tree, but we are taking into consideration a very simple game tree. All right, so look here. At the terminal nodes, there are certain values that are associated with each of these terminal nodes. Now, these values are nothing but the utility values which describe the value of the outcome of the game. Some values are having negative values, as you may see. Some values are having positive values. Now, we will be using these values to describe the overall outcome of this game. All right, now that you have understood this game tree, let us come back again to the beginning part of the algorithm. Now this algorithm uses recursive or backtracking algorithm. All right, now this algorithm does not only belong in the domain of artificial intelligence or classical AI, but it is also used in decision making, and it is used in the area which is known as game theory. Game theory is an interdisciplinary area actually. So what this algorithm gives us is it uses recursion to search through the game tree. All right, in this algorithm, most importantly, two players are associated with this game, max and min, which I have described before. Now the game is played in such a manner that max should get the maximum benefit or the maximized value, and the vice versa for min. So for exploring this game tree, the algorithm will make use of DFS, depth first search, that we described in the previous classes, right? So let me show you the algorithm now. Don't worry if you can't see the full structure of this algorithm. Actually, I'll be describing in the PDF also. So how this algorithm is designed is, it should be designed in a recursive manner. So just like any algorithm which may be implemented on any binary trees, given here is, in this algorithm it requires three arguments. The first argument is the current node that we are processing. Depth is the depth value for the current node that is present, the current depth at which the node is present. Then there is another argument which is known as which is called or referred as maximizing player. So this maximizing player is of type boolean. Okay, you must remember this maximizing player is of type boolean. So if it happens to be a boolean, there is only two values that it can actually take into account. Either it may be a true boolean or false. Alright, if it happens to be true, then we are going to take into account that it is the turn for Max to play the game. If it happens it is false, then we should take into account that it is the turn for the mean player to play the game. Now, at the first instruction of this algorithm, what is given here is, if the current depth at which we are interested happens to be 0. What does this mean? It also means that the node that we are taking interest happens to be a terminal node. Then we don't need further exploration of the tree. Right. So for any general class of recursion algorithm, what we have is, before the processing step, we also have a base condition or termination step. So this part of the algorithm is actually the termination step of this algorithm. So given here is, if the node happens to be a terminal node, then what we have to do is we have to just return the static evaluation of the node, which happens to be the current utility value, current values that are associated with each of these terminal nodes, which will be returned. All right. So in the next step, we have the step for Max. When Max plays the game, what it actually happens? If maximizing player happens to be true, then it is the Max player's turn to play the game. Now what happens here is, we have a variable which is known as max eva. So here, before we actually begin, it is assigned minus infinity. So remember, in a program we cannot just write like minus infinity. This infinity should be a fairly large amount. Alright, like a large integer like 99999 or something like that. So this will be the value that will be assigned to max eva. So what happens here is, for if that current node that we are assessing has a child, then we will go through this for loop. Alright, now for each child of the node, what we will do is, we will recursively call the minimax function. Alright, when we call this minimax function, what happens, I will give you the recursive call structure over this tree also. So we will be recursively calling this function. What happens here is, we will be exploring the further depths of the tree. Alright, for each of those nodes, when we explore till the terminal nodes, we will perform the maximum value evaluation. Alright, this max function is nothing but it finds the maximum value between max eva and eva. Alright, so we will return the maximum value. Alright, when it is the turn for the mean player to play the game, similarly we will use the variable mean eva, another variable. Alright, further we will further explore the tree. Then for this, if it is the turn for the mean player, we will return the minimum value between mean eva and eva. So let me show you the recursive call structure for the tree so that we make things easy. Alright, so when we implement this algorithm over this particular game tree that we have taken into consideration, what happens here is, this recursive call structure takes into place. Alright, so when we begin with max, the current node initial call for the this algorithm will be, node will be a, depth will be 3, and the boolean value will be true. When this call is made, we have a recursive call in the function for the max player also. When that happens, two further instances come into picture, which is b and c. The current value becomes 2 and 2, so the current boolean value will be false, which makes the turn for the mean player. When we further evaluate, this b generates into d and e at depths 1 and 1, and the boolean values get translated into true and true. So further C is further evaluated, F and G are further F and G are further explored. Now when we try to explore further from D, we get the terminal nodes. What do we get? We get the terminal nodes of H and I. Alright, so since this happens to be the terminal nodes, what does the algorithm do? It returns the static values which are associated with this. So we have taken -1 and 4, similarly 2, 6, -3, -5, 0, 7. So before looking this into picture, I'll further this explain the working. So now that you have seen the recursive call structure, don't worry, I will share in PDF mode, don't worry about this. So here the algorithm applies DFS, defer search. Okay, now at the terminal nodes the terminal values are given, so we will compare those values. So step 1 is for what? Max starts the play, right? So step 1 is supposed to be for the max player. So what happens here is when max reaches node D, all right, from D when we further evaluate, we have the terminal nodes which have again static valuation numbers associated with them. So this max -1 and minus infinity will generate max -1 and 4. So for further understanding I have given here. So since in a recursion we discussed in the previous lectures and also in the previous courses in the previous semesters. So what happens is when we call a function as a recursion type, the values are returned in a bottom up fashion. Alright, so bottom up fashion. So when we have this, if it was for the turn of max, then we need to return the maximum value between -1 and 4. So the maximum value between -1 and 4 happens to be 4. So the current evaluation of D is returned as 4. For E, we need to take the maximum between 2 and 6. So the maximum value between 2 and 6 is 6. So 6 is evaluated or returned back as 6. So -3 and -5, we take the maximum between this. We know -3 is the maximum. So we also return the maximum between 0 and 7, which is 7. Now that we have reached or we have assessed the values for D, E, F and G, now we know that this happened from the mean player's call. So what we do is we take the minimum between 4 and 6. Alright, 4 and 6, which returns as the current evaluation for B. And we return the minimum between -3 and 7, which happens to be -3. Now when we return this value, the first call was made by the max player, so we will be returning the maximum value between 4 and -3, which happens to be 4. So the total or the cumulative or the final outcome of this game is 4. Got the idea? So I have illustrated in the steps here. Alright, so I'll be giving the notes for understanding this algorithm also. And let's just come to the properties of this algorithm. Alright, okay. The algorithm is itself complete. Alright, it will find a solution if the search tree happens to be finite. So it is complete in nature. Any game that we are going to consider is supposed to be a finite game. That means the game can be played with finite number of moves. Number 2, it is optimal only if the opponents play fairly to each other. Okay, now The time complexity for this algorithm is order of b to the power m, where b is the branching factor of the tree, where the current branching factor for our tree is what? What is the branching factor of our tree? We have 2 branches, so that makes it 2. There might be other situations where the branching factor is greater than 2. And what is m? M is the depth of the tree. Alright. Now the space complexity is order of b into m. So these are the things that you need to understand about Minimax algorithm. For further reading, I will be sharing these notes in PDF form. In the next session, we will discuss alpha beta pruning algorithm. Alright, and we will assess where there are any pros and cons for this Minimax algorithm. Then we will proceed to alpha beta pruning. Thank you. And if you have any further questions, you are supposed to ask me. You are not supposed to keep in with yourself. Alright? It is not healthy. Okay. Thank you.